welcome to the 31st Gardner Lecture. I'm Wesley Harris, head of the Department of Aeronautics and Astronautics, and I have the distinct honor of not only welcoming you to our 31st Gardner Lecture, but to share some background as to the naming of this distinguished lectureship. It is named after Lester Gardner. Mr. Gardner was born in New York City in 1876. And those of you who are history buffs realize that's the same year in which U.S. General George Armstrong Custer was killed in the Battle of Little Bighorn. But that didn't stop Lester. He found his way to MIT and earned his Bachelor of Science degree here at MIT in 1898. He left MIT and proceeded to study law at Columbia University. And then he really made his switch to technology and became quite active in radio broadcasting, including arranging the first demonstration of ship-to-shore radio telephone operations with David Sonoff on the receiving end. As you know, David went on to lead RCA. Lester then made some serious contacts with the leadership of aviation in the U.S., having recently met Glenn Martin and our own Professor Jerome C. Hunsaker. The three of them organized the Gardner Publishing Company. Shortly thereafter, the war, the First Great War, began, and Lester proceeded to the rank of major, including organizing 89 aero squadrons that were sent overseas, and he organized these squadrons at Kelly Field in Texas. Following the war, he became a major figure in aviation in this country, serving as a delegate to several international conferences, Rome in 27, back in Washington, D.C. in 28, Berlin in 29, and again Rome in 1938. He then organized the Institute of Aeronautical Sciences in 1932, and later with the American Rocket Society, IAS, became the AIAA. Mr. Gardner was instrumental in creating the Hunsaker Professorship at MIT. He became an honorary fellow of the Royal Aeronautical Society of London. He was a fellow of the Institute of the Aeronautical Sciences in the U.S., and he received the Guggenheim Medal in 1947 for outstanding achievement in advancing aeronautics. Now, for the main course. It is my distinct honor and pleasure to introduce Dr. Harrison Jack Schmitt, who will talk to us today on Trip to the Moon and the Legacy of Apollo. Jack is a geologist, a pilot, an astronaut, an administrator, a business person, a writer, and a former U.S. Senator. He assured me that he also loves to play squash. Born in Santa Rita, New Mexico, he never found his way to MIT, but he did to Caltech, where he earned his Bachelor of Science degree, finally finding the East Coast, somewhere in Cambridge, earning a PhD. Okay. Down the road a little bit. Jack is a fellow, or honorary fellow, in at least 9 technical societies, including the American Institute of Aeronautics and Astronautics and the American Astronomical Society. He has more than 30 special awards, including honorary degrees. I've picked only a few of them. For example, Jack received the Republic of Senegal's National Order of the Lion in 1973. He is the first Sherman Fairchild Distinguished Scholar at Caltech in 1973, and he received the G.K. Gilbert Award bestowed upon him by the Planetary Geology Division of the Geological Society of America in 1989. He was selected as a science astronaut by NASA in 1965. He was a lunar module pilot in Apollo 17, which left Earth on December 6, 1972, and returned on December 19th. Under his control, it landed in the valley of the Taurus Littoral. Jack is the only scientist and the last of 12 humans to step on the moon. He continued his distinguished career of service, having been selected as U.S. Senator from the state of New Mexico from 1977 to 82. He is a member of our family in that he serves on the corporation of the Draper Laboratory. He's also a member of the Corporation of Orbital Sciences. Jack?
Well, thank you, Wes. And I guess I did not realize that someone standing here 31 years ago was just preceding a flight to the moon, which occurred about a little over 30 years ago. And what I'm going to do today to start things off and have a little fun is show you about 10-minute video of most of a trip to the moon. It's obviously quite compressed, but I think you'll enjoy it. And then we'll talk a little bit about what all of this may mean in various ways to the past as well as to the future. This video I put together for our 30th anniversary celebration at the Smithsonian Institution last December. And unfortunately, they didn't equip me with a checklist, so we'll see what happens. There we go. This, you'll have to suffer through my narration and maybe a little sound in the background. Those were the patches of the various Apollo missions that did indeed go to the moon. All the missions, and at least all of them, but particularly the later ones, had a great deal of science training. We put in 3, 4, 5 days a month of exploration training, often using the operating version of a lunar rover, but also all the equipment that we would have. So the use of that equipment became second nature as possible, and we could better employ what some people thought was a reason for sending people to the moon, and that is their minds. Getting suited up on the before launch, we were scheduled to launch at about 10 o'clock on the 6th. We actually had a 2-hour and 40-minute delay, leaving Earth on December 7th. Here you see Ron saying goodbye through his helmet to his wife, Jan. Gene trying to hurry us along. As usual, I'm bringing up the rear. Charlie Buckley closing the door on us, but I had second thoughts, I guess. And he wouldn't let me out. Maybe I just needed to visit a restroom somewhere, I don't know. The launch of Saturn V is truly spectacular. At 6.8 million pounds, 7.5 million pounds of thrust at this point, and very, very slow acceleration initially, getting to 4 Gs at 2 minutes and 45 seconds, and then staging and a steady 1.5 Gs the rest of the way. We had great, outstanding views of the planet Earth throughout our whole flight to the moon. This particular sequence may remind you of Apollo 13, the movie, where we were docking. Ron was docking with the lunar module, so it would go along with us into to the moon. Wouldn't make much sense to go without it, I wouldn't think. Although Apollo 8 would disagree with me, they had a great time without it. Landing, this pitch over occurred at 8,000 feet, and if you look very carefully, we've got, I'm sorry about the lights. I hope you have a better view of this than I do, but you see the shadow of the lunar module up there. That is in the zero phase point, sun directly behind us, and now you're seeing the shadow get closer to the surface, and we had touchdown. Streaming away, I hope you can see the streamers there. That's the dust. Great deal of dust in these in the lunar debris. About 60%. Gene asked me to come. About 60% is less than 100 microns. Gene had asked me to come over and help him get a drill core out of the surface. He learned to regret such a request here, as you will see. This was our first excursion. We're still getting used to 1/6. I am still getting used to 1/6 gravity. This is the second excursion, and you can, and the only time in the whole mission that I did individual sampling. We usually worked as a team, as you'll see later, and I have already dropped a bag full of samples, so I'm getting that up and leaning back. You can see I've done this before. I'm quite dirty, and I just forgot how to hang on to that sack. Now I'm getting a little bit upset. And about this point, I was informed that the Houston Ballet Society was interested in my services. And so I figured a better demonstration was appropriate. And you'll see that here in just a moment. I finally got my sack, headed for my tool. Here, now this is an actual demonstration of ballet style on the moon. Now you, of course, fall on my face again. Now, a much better way to operate on the moon, you see here at the location where we found the famous orange soil or orange pyroclastic glass. That was a trench I had dug right in there. Working as a team, Gene always got the sample bag a little bit too high for me, but still, that's much more efficient than what you just saw a few moments ago. This glass, as we will talk about a little bit later, has become a very, very important part of the Apollo legacy, in that it is calling into question some of the consensus opinions about the origin of the moon and some other aspects of lunar evolution. This was not totally unexpected discovery. Here you see that deposit. It's in the rim of a crater called Shorty. This is a gnomon for photographic control over here. And that's a pretty good color representation. Actually, a little bit red. It should be redder here in the middle and a little yellower here. But that's about the best we've been able to do so far. Down in mission control, a variety of people, including Jim Lovell right there, were watching over our shoulder. We never gave them a chance to tell us to do much, but nevertheless, they felt good about being there. Now, Gene had a certain technique, as did most of the pilot astronauts. It must be genetic. They like to hop across the surface. They call this their bunny hop. As you can see, even it is not too successful sometimes. And in a few moments, you'll see how really it is to work across the lunar surface. The best way to do it, but that'll be a moment or two. Now, the camera's on me taking a pan. If you look carefully, there's my face. It's one of the few faces, if not the only face, to be photographed on the moon, because I kept my visor up. Being a good geologist, I wanted to make sure I saw the rocks as clearly as possible, and so the gold-plated visor spent part of its time up. Now, this is a little skiing demonstration, a little parallel skiing. Not too good. As you can see, you can catch an edge every once in a while. Now, more appropriately for moving across the moon is using a cross-country skiing technique. And here you see that technique applied, gliding above the surface, running through a boulder field. This was on our third excursion, and you can see we had a great deal of confidence by this time to go running like this. And really, that ultimately, I think, will be the mode of transportation of choice. You can, over a reasonably level surface, you can probably get up to 10 or 15 kilometers an hour that way without expenditure of much effort. Departure from the moon, not a really good photograph. Gene tried to persuade me to go outside and get one, but about a half a G acceleration, and we're off. The camera I had mounted in my window, looking down now at the surface. There's the descent stage, our launch platform, our tracks going back and forth to an antenna I laid out here, and to the ALSEP. Ron Evans now taking these pictures as we approached rendezvous. We had a very rapid rendezvous. It was what was called direct ascent rendezvous. Ron now going outside for his spacewalk. Actually, space swim is a more appropriate term because you really do pull yourself along and don't use your legs at all. Of course, high mom is required. And this was about an hour-long spacewalk that he had to gather canisters of film that had been exposed during his 3 days of orbiting operations, independent of our activities on the surface. I was here in the hatch helping to try to keep him from getting tangled up in that umbilical, which, as you can see, has a life of its own. He would hand me the canister, I'd stick it down and hope that Gene could keep it from flying out into space. And so we were reasonably successful at that. 3 days after we left the moon, we entered the atmosphere at 35,000 miles an hour, pulled about 7 Gs to make sure we were captured, and then flew our way down to where the carrier was waiting for us. The Navy actually parked their carriers about 5 miles away from our planned impact point, afraid that we might land on their carrier. I thought that was not very nice. But splashdown of the final Apollo mission, and certainly the most recent flight to the moon, you see here is photographs taken from a helicopter that almost immediately deployed Navy SEALs, who then put a flotation collar around the spacecraft as a safety precaution. And here, I think this may be Gene Cernan, the last to leave the ship. Actually, I think Gene left first. That was sort of a non-Navy tradition. Now, I hope you caught quickly, Gene and I both grasped the railings of the steps there because you really do have some trouble balancing. Ron wandering all over the red carpet there is near the end. The Apollo heritage is really quite remarkable. I think history will be very kind to it for what not only was done but what was learned. Maybe one of the most important parts of what we left, at least at our site, was a map of where all the Apollo landing sites are. That was something I insisted that we have on that plaque. Then also the legacy of having this view here in a moment of our planet Earth from 34,000 miles away on our way out to the moon. Really a remarkable photograph, still the most requested photograph from the NASA archives. And with that, I'll see if I can turn this off. Did that work? Now, let's see if I may have destroyed the whole process here of getting the PowerPoint presentation up. There we go. The legacy of Apollo comes in many, this is a little more serious part of the discussion, hopefully not too serious. It comes in many aspects. Certainly, it was born of the Cold War. And the political goals of both Eisenhower and Kennedy were met by it in its ultimate form. I include Eisenhower here, not because he provided the main impetus to Apollo. Kennedy certainly did that. But if Eisenhower hadn't insisted personally on the development of the Saturn V launch vehicle and associated engines, it wouldn't have happened. And so he does deserve maybe a little more credit for this than he has gotten normally in the history books. There really is a dichotomy in what Eisenhower apparently felt about said publicly about putting men into space, and certainly to the moon, and what he did to ensure that we had a heavy lift launch vehicle which had no other purpose but to put men in the vicinity of the moon. So I'll let you figure out exactly what was on his mind in doing that. The leadership of the Soviet Union, I think, was clearly intimidated enough so that Reagan's strategic defense initiative later became credible. Literally, America could succeed where the Soviets apparently could not in such an endeavor. U.S. pride and confidence was enhanced in a time when, as you recall, the missile gap and other things were creating a bit of unease in the United States among its people. And as I traveled the world through many years later, I found that there was a promise, at least, to other peoples of the world that their future could be better than their past. I'm not sure we've fully lived up to that promise as yet, but still it is there. Now, the cultural legacy is somewhat interesting as well. The Apollo created a new evolutionary status for humankind in the universe. There was a rapid improvement in the human condition on Earth due to the acceleration of technological expansion. Again, it probably would have happened, but certainly much more slowly than it did. Future terrestrial energy and environmental improvement is now possible, both with the increase in conversion efficiencies of ordinary energy sources and with the new potential of lunar helium-3 fusion that we'll talk about a little bit more in a few moments. And indeed, on the moon at least, we've identified clearly space settlement resources, hydrogen, oxygen, and water, and then ultimately, I think, food as well for space settlements. There are not resources that would have a value here on Earth, but certainly would have value to future inhabitants of space. The keys to the success of Apollo comes in many different forms, and you have to think of these as the kinds of things that have to be in place if we are going to do these kinds of things in deep space or take on major significant projects anywhere. A sufficient base of technology certainly came from the World War II, the Cold War, and the decisions that Eisenhower made during his second administration. There was a reservoir of young engineers and skilled workers that the 1957 launch of Sputnik generated. The pervasive environment of national unease, some of you are old enough to remember that that did exist, particularly in the campaign of 1960. There was a catalytic event, of course, that brings focus to the effort. That was presaged by the Sputnik launch, but the one event that really began to focus the attention of the Kennedy White House was Gagarin's flight in April of 1961. And we had, at that time, an articulate and trusted and persuasive president who actually had been thinking about this and was preparing himself for this well before Gagarin's flight, that is, at least weeks before, in some of the decisions he made on the budget cycle in discussions with Jim Webb. And we, after the Apollo 204 fire at least, we put together competent and disciplined management. Management was moving along quite well up to that point, but still not at the point and level necessary for operations in deep space. Again, I would submit to you that when you work in deep space, at least for the foreseeable future, most, if not all, of these conditions are going to be required. Now, because of its currency, let me just digress slightly here relative to NASA's worst accidents. And there are, I think, some common threads. The Apollo 204 fire, the Challenger and Columbia accidents really began with the acceptance of abnormal as normal. We also at the time had a lack of a technically experienced administrator. Whether that's significant or not, I'll let you decide, but all three have that common thread. The lack of a top-level managerial and operational oversight taking place was not happening under Webb, and it was not happening in the case of the other two. And a lack of a mechanism for appeal in the chain of command of management. I'll tell you one thing about Apollo. There was always a way to get a good idea moved up. That stopped pretty much at the end of Apollo. Good ideas did not move easily through the system. I had many experiences of my own. I saw many others where engineers, astronauts, scientists at any level, if they had a good idea and and that idea would stand the test of discussions with their colleagues, that would move up and through the chain of management. Very, very important to have that in these kinds of very complex programs and projects. Now, only with Apollo 13 do I think you can see a pure set of accidents and design flaws that can be blamed, where we just did not anticipate in the design and in the operation a number of things that could go wrong all at once. And that really is the background of the Apollo 13 accident. And one of the reasons why it was fixed reasonably quickly and we got back to flight quite quickly as well. Now let's talk in more detail about the scientific legacy. A first-order understanding of the origin and evolution of the moon clearly has resulted from Apollo, and of course the later unmanned programs such as Clementine and Lunar Prospector, with a nice assist from Galileo as well. May it rest in peace. We had developed a basis for the interpretation of that post-Apollo information about the moon by the analysis of the lunar samples from Apollo. And that in turn became the foundation for comparative planetology. Comparative planetology really wasn't much. There were a few people like Kuiper and Shoemaker around who considered themselves, I think, planetologists, but as a discipline, it was not active. Very quickly with Apollo, and even before Apollo, but in anticipation of it, comparative planetology became an important discipline. There is recorded on the moon a record of the history of the inner solar system. And it is a guide to the early history of the Earth and Mars. And that is particularly a record of the cometary asteroid impact history of the inner solar system. We also have delineated a lunar resource potential, not only for use here on Earth, but also clearly a potential for use in space, and not just on the moon, but elsewhere. And that's not too shabby a legacy scientifically, in spite of what some of my scientific colleagues might try to paint. Now, just to give you an idea of what we have learned about lunar evolution, and just remember, this chart really could not have been created without Apollo. We certainly have learned about the beginning. The age of the moon is roughly that of the age of the solar system, not exactly, and it's in that not exactly that things really are starting to get exciting. There is a debate, and most of the debates I have now here in red, of whether Earth impact or capture has resulted in the origin of the Earth's moon. The consensus, 95% or more of the people in my community of planetologists would say Earth impact, that is the impact of a Mars-sized asteroid, resulted in the origin of the moon. I'm not one of those that agree with that. I think there's some major problems, and we'll talk about that in a moment. One new concept that came out of Apollo very soon after the Apollo 11 samples were analyzed, both John Wood at the Smithsonian Observatory here and also others immediately realized that the moon had differentiated. That is, there had been a magma ocean that had crystallized in sequence and had resulted in a chemical differentiation of the elements in the crust of the moon, or in the upper mantle of the moon, down to at least 500 kilometers. That magma ocean was a new concept. That is now being considered as a viable concept on all of the terrestrial planets for this period of time. There was a residue from that magma ocean that has come, unfortunately now is called ure-creep. Creep is potassium, rare earth elements, and phosphorus-rich material. Ure means the original creep, because all we see at the surface of the moon is creep that's not original. It's just the signature of it. I'm sure that excites you very much. Then there comes this important cratering history that we now have. And in that, maybe one of the most important aspects is the definition now on the moon of continental scale basins. I'm talking about basins that are 2,000 kilometers in diameter or more. And these are basins that formed on the moon and almost certainly formed on Earth as a result of the impact of extraordinary energetic objects from space. There are many other basins, large basins. There's something like 45 or 50 of these large basins which are greater than 300 kilometers in diameter. The oldest of these have apparently resulted in the crust of the moon being strengthened as the liquid that we call the residual liquid from the magma ocean, the so-called creep, moved up into the basin and solidified, because the last 14 or so of these large basins have mass concentrations in them, which have been supported now for almost 4 billion years. So the crust has to be extraordinarily strong for that to have occurred. Coincidentally, it also appears that during that period of young basin formation, the core of the moon was active, and that we actually have evidence now of remnant magnetism on the far side of the moon at the antipodes of these young large basins that presumably indicate that a circulating core dynamo was present during this very brief period of time, maybe no longer than 100 million years. Now this is another area of great controversy within our community, is whether or not that period that I indicated there, maybe 400 or 500 million years of cratering, didn't happen all at once. And that is one of the primary rationales for the proposals to go to the far side of the moon, to the center, near the center of the South Pole Aitken Basin. That is a basin 2,500 kilometers in diameter, to see if we can't resolve some of these questions about whether you had about 100 million years of intense impact activity on the moon about 3.9 billion years ago, or whether it extended over 400 or 500 million years. Either way, these large basins do represent a new source of debris in the solar system, entering the inner solar system, that we really hadn't been contemplated before. We generally have thought of some kind of continuum of impact activity in the inner solar system, dying off gradually with time. Here it appears that particularly if it is a single cataclysm of 100 million years duration, something happened in the outer solar system to begin to send objects into the inner solar system much more frequently, large objects much more frequently than it happened before. One of the very intriguing possibility. Now, during this cratering period, there appears to have been significant deep igneous activity in the moon, probably the result of pressure release due to these large impacts on material that was almost at the melting point anyway, and those so-called MG sweet magmas moved up into the crust. I'm not going to spend a lot of time on that. The next major episode was the formation of basaltic maria, those dark parts of the moon that form the image of the man in the moon or the rabbit in the moon or whatever character you happen to see on any particular evening, and depending on what you were doing. Early in that period, the so-called cryptomaria have been identified. These are covered by the ejecta from the young large basins, so that's why they're called crypto. We only see hints of them because of other small impact craters that have exposed them. The main Maria episode was between about 3.8 and 3 billion years ago. Then it began to die off gradually with time until using crater counts, estimates of age using crater counts, crater size frequency counts, we think that there may have been igneous activity in one part of the moon as little as 1 billion years ago. But realize that almost everything that I'm talking about here on the moon happened a long time ago. And it gives us a window into the early history of the Earth. Now, I'm not going to go into this other than to show you this diagram to indicate that if you just look at the first 50, 60, 70 million years of the history of the solar system, we are learning a great deal about what was going on. And not a small part of that is a result of what we have learned of the moon. In particular, the Apollo legacy extends to the issue of planetesimal aggregation in the inner solar system, on through the development of these magma oceans, protocores of the terrestrial planets, and then also the issue of, down at the bottom here, of when did the cores of the various terrestrial planets actually aggregate. We know a lot about when core-forming materials separated in the terrestrial planets, but I submit, is a separate issue of when you actually formed a core. We actually, using the reason we can get into all of these kinds of issues now is because of the identification a few decades ago of what are called extinct isotopes. These are isotopes that have very, very short half-lives, decay to a definitive daughter product that you can now measure. You don't see the isotopes anymore, but you see the daughter product. Aluminum-26 is one of the more important ones, about a 9 million year half-life. Excuse me, about a 720,000 year half-life. Hafnium-182 is another one that has the 9 million year half-life. This is one of those, identification of those isotopes and the ability of mass spectrometry to measure extremely small amounts of materials, literally atoms, is giving us this kind of an opportunity now to understand the formation of a solar system around a sun-like star. Really, really exciting time for people who are in this field. Now, let's go back to this business about giant impact. It's a very attractive hypothesis in that it explains one thing very well, and that is the high angular momentum of the Earth-Moon system. However, it can't explain, in my estimation, the geology and composition of the lower mantle of the Moon. The challenges that it has is that we are seeing increasingly, particularly in the analysis of the orange glass that I showed you in the video, and a green glass that was belatedly identified in the Apollo 15 sample suite. In those, we are seeing evidence that the lower mantle of the moon, that is the part of the moon below about 500 kilometers, has never melted in its entirety, never differentiated, that is crystallized separate crystals, minerals, and it has chondritic signatures in it, particularly for tungsten, for lead, and a very high volatile content relative to anything that we see at the surface of the moon. The seismic evidence and trace element data suggests that you have increased alumina as a result of the lack of differentiation. Garnet present below 500 kilometers. I see Jim Thompson in the audience. You'll know that I'm always interested in finding garnet somewhere, having done my thesis in related kinds of rocks. And these kinds of issues are ones which so far the proponents of the giant impact theory have not been able to deal with. They are trying, and by increasingly complex models, but I think that when the final result is in, when we finally know more than we know probably right now, that we'll find that the capture of an independent co-orbiting small planet seriously needs reconsideration. That does have some problems, at least based on the little bit of modeling that's been done to date. What is really needed in this question is for some very, very bright graduate student, hopefully one in this audience, who will undertake to begin to model capture now in a much more systematic way than it's ever been done, and at least become competitive with the level of computer modeling that's done for the capture hypothesis. Now, I do think, though, that this issue of the very large basins is one of very great importance to terrestrial geologists right now, and we'll get into why in just a moment. These are some of the basins that are non-controversial. The South Pole Aiken Basin, which you don't see well in this picture, but is right in this area, is attested to by all workers in the field. The Procolarum Basin, Don Wilhelms and I and a few others think is an even larger basin that has been seriously modified by other impacts. There's a hint of this prospect, what I call the Prospector Basin, in some of the data from Prospector, the same for Clementine Basin here, and maybe a cryptic far side small topographic anomaly there. The statistical analysis of the frequency of these large basins for a body the size of the moon suggested to Don Wilhelms that we should have seen about 14 of these. I've only shown you the possibility of 5 here, and those kind of analyses are always subject to some debate, but nevertheless, however many there are, they almost certainly occurred on Earth as well. And here you see a topographic representation of those basins. Now South Pole Aiken becomes much more obvious as an immense topographic low. The lowest point here is 12 kilometers below the mean lunar radius. It really is one heck of a hole for the moon. Even Procolarum shows a general topographic low there as well. Now, these large basins may well relate. Some of you in the audience will know that people in our field talk about the creep hotspot. That's a concentration of this potassium rare earth element phosphorus material on the front side of the moon that may well have been caused by the migration of the residual liquid to a low pressure area. We already talked about a little bit about the MG suites through pressure release melting, and also there's an issue of an ilmenite, that's an iron titanium oxide rich cumulate that may have overturned under the Procolarum event to give you these young Mari I mentioned that are about a billion years old that are also titanium rich. Those are fairly detailed issues that we don't need to go into today unless there's some additional interest in it. More importantly are these continental scale basins. My estimation is that they were forming on the moon and all the terrestrial planets between about 4.2 and 4.5 billion years ago. One of the more interesting aspects of that is that just recently, in the last 2 or 3 years, workers have been able to identify 4.4 billion year old terrestrial zircons. Zircons are very stable, hard minerals that seem to last forever. under proper circumstances, and in some of the oldest sediments on Earth, we are finding detrital zircons, that is sedimentary zircons, the cores of which show ages of this kind. In the 4.4, 4.3 billion year old. That again shows you what mass spectrometry is able to do these days on a single crystal of zircon, give you an age of this nature. But the thing is, where do they come from? And certainly it's in the same time frame as at least my estimates, and I think Wilhelm's estimates for the ages of these large basins. Zircon is a product of late stage magma differentiation here on Earth. It's a very familiar mineral to us. Water would increase the amount of terrestrial impact melt volume from one of these large impacts, and a differentiation of that impact melt may well have resulted in these zircons. And as a matter of fact, the oxygen isotopes of the zircons are consistent with water in the magma from which they form. So I think we're beginning to bring those two stories together slowly, and it's a very exciting story indeed, because it begins to create extraordinary diversity in the Earth's crust right almost from the very beginning of Earth history. And of course begins to even relate in some indirect ways to the questions of the origin of life. Now the old large basins, in general, the ones greater than 300 kilometers in diameter, we've talked about them a little bit. The Apollo 11 site is in one of them, that's Mare Tranquillitatis down here. The Serenitatis Basin, which is a young large basin, Apollo 17 landed right there. It's here. This is another, this is Fecunditatis, another old large basin, not nearly as distinct as these younger ones. These all have mascons in them, these do not. They do have a mare fill, but not as thick in the old large basins as you would expect. Now the issues here, I'm not going to spend your time on these. These are, again, issues that will be of interest to some in the audience, but I'm sure not all. It had to do with the strengthening of the crust as a result of these the old basins. We talked about the cataclysm, and I'm not going to dwell on that further. But we might talk about why I think the cataclysm is an artifact. It's an artifact of these late young impacts. You had some 14 of these, which distributed ejecta throughout almost all the moon, caused a great deal of resurfacing, and I have a feeling that that's what most of the evidence of this so-called cataclysm is telling us. We will have to wait and see. There are some other ages at Apollo 16, Apollo 17 sites that suggest that older impacts did indeed occur. I mentioned the global effects of the young large basins on this age bias for the cataclysm. There is ejecta covering the Cryptomaria, which is global. No question the ejecta from those later impacts was global. And there are a few of those samples, as I mentioned. Now, I do want to, though, emphasize the importance in the studies of the history of the solar system to begin to think about what the source of these impactors were, whether it was 100 million years or 400 million years. I see the PC now is reacting to my Mac-generated PowerPoint by spelling out every sentence. There's certainly some new accretionary reservoir appeared. The sources to consider would be the Oort cloud, which through an interaction of a passer stellar body, the Oort cloud being the potential source of long-period comets. Of course, nobody's ever seen an object in the Oort cloud, but it has pretty well established itself as an article of faith that it's out there. Maybe more important to look at is the Proto-Kuiper belt. Interaction with the large cometary objects we have out there. Some 800 now have been identified. There are more than 100 kilometers in diameter, I think. So we know they're out there. But as the gas giants evolved in their orbits, they would influence the orbits of those cometary objects and may well have caused them to be injected into this inner solar system. Main belt asteroids. Jupiter interaction with the planetesimals that formed in the asteroid belt and the expulsion of the fragments from that belt may well be another source, or some combination of at least 2 and 3 and maybe even all of these. The Now, the implications of intense cratering on the Earth and Mars, I think, are quite important to consider. This is what the far side cratered highlands look like. We have the southern uplands of the moon show much the same character. This just happens to be a picture of the far side highlands. They're saturated with craters 60 to 70 kilometers in diameter. Saturated, mathematically saturated with craters of that size. So you can imagine the level of violence that was taking place. It created a megaregolith some 25 kilometers thick. It's well mixed on the scale of hundreds of kilometers, and with a significant implantation of solar wind hydrogen in that material. I suspect that in a hydrous environment, a planet with a hydrous environment, such as the Earth and Mars, that clay minerals were the dominant mineral species at this time. Because that's what happens to minerals that you grind up, vitrify, and put in a water environment. They turn to clay. And I think it's important that we think more about just what it means to have that kind of a mineral as your dominant mineral species at the surface of the Earth and indeed of Mars. The implications of all of this may have a great deal to do with life. Certainly a general impact, intense impact environment from 4.5 to 4.2 billion years. We had clays, possibly sulfides in various environments that were dominant in hydrous environments up to 3.8 billion years. 3.8 billion years is the end of the major cratering period in the inner solar system. Global soup for organic synthesis as a result of this. Clearly there must have been organic molecular synthesis on Earth prior to 3.8 billion years. Mineral catalysts, I believe, were very probably involved in this synthesis. But large basin formation up to 3.8 billion years prevented any systematic development of replicating life forms. It wasn't until the large basin ceased to form that we start to see evidence of replicating life forms on Earth. And that is just almost exactly, well, within those limits, right at about 3.8 billion years. Fossils at 3.5, but isotopic evidence of life processes underway at about 3.8 billion years. So I don't believe that is coincidence. The end of the large basin formation suddenly allowed replicating life forms to actually take hold. They may have taken hold before, but may also have been wiped out. The geochemical heterogeneity in the Earth crust we've already mentioned. The zircons, I think, show that now at 4.4 billion years. An important part of this whole picture. Clearly global hostility to life prior to 3.8 billion years, but a continuous compatibility for life after 3.8 billion years. Yes, there were certain points where the species of the Earth took a beating, and at certain points in geologic time after that, but I doubt if it would have been possible for anything happening in the solar system to have wiped out life on Earth after 3.8 billion years. Now let's talk a little bit finally about this access to our lunar resources. It's not a pure science issue, but it does relate to one of the most serious problems affecting the world today, and that is we're going to have something like 10 billion Earthlings by 2050. Excuse me. Let you think about the implications of that number. It may even be larger. That implies, and this is my estimate, something like a factor of 8 potential increase in energy demand. How do I get to that number? Well, a factor of 2 to stay even with the 2000 demand. And you can pick your own number. I pick about a factor of 4 or more to meet the aspirations and of developing countries and to slow population growth. Now, you might want to add an X factor here to mitigate climate change. Whichever way climate goes, warmer or cooler, technologically the way you mitigate it is with energy, mitigate its consequences. So there is some very large factor that's result in an increase in energy supply. Now, I think you've all seen this picture. It's useful in various ways. It certainly shows where energy is being used and where it's not being used. It's essential, certainly, for the health, economy, and safety of the United States. and I would submit for the preservation of our freedom. If we are not able to continually increase our use of energy, I think we're going to be vulnerable to many, in many different ways. But we are also vulnerable if we continue to use it in the way we've been using it in the past. Now let's talk about some fusion fuel cycles as they're relevant to the moon and to what we found on the surface of the moon. The first generation fuels, most of you will be familiar with. It's been the focus of billions of dollars of federal and international effort to develop a deuterium-tritium fuel cycle using tokamak technology primarily, where your primary reaction product is a neutron that is then captured in the walls of a reactor and converted to heat and then converted to electricity, the heat converted to electricity. Another first-generation cycle that isn't very popular because of its very high neutron flux is deuterium-deuterium. It does have some other applications for developing neutron sources and the like, but it still has to be considered one of the first-generation fuels. Second-generation fuels are not being looked at by anyone systematically other than the group we have at Wisconsin that I'm aware of, although we don't know what the Chinese are doing. And right now the Japanese are more interested in the deuterium-deuterium cycle. Deuterium helium-3 has a great advantage because theoretically what you get out of it is a proton, which is obviously positively charged and controllable and does not create the problems neutrons cause in the creation of radioactive and damaged first walls. A third generation fuel, theoretically again, is helium-3, helium-3. That has not been demonstrated to my knowledge as in terms of a fusion cycle, but we expect that we will probably have such a demonstration within the next few months at Wisconsin using a new machine. That is even obviously more advantageous because of the increased number of protons produced, which again can be converted directly to electricity. Now, at Wisconsin, we have this laboratory kludge device, which of course no one at MIT would ever be caught dead with a device that looks like this, built at the products left over from other research experiments. We have just been working to have a much nicer looking device you see here, thanks to the initial design work done for the Marshall Space Flight Center. They no longer are apparently working in this field, but the company that built a device for them built this for us with some modifications. And this will be used for our helium-3, helium-3 research without putting any deuterium in it at all. This gives you maybe a feeling for what it looks like to look into one of these IEC devices, inertial electrostatic devices, where you have an outer grid and inner grid with a potential across them, across which you accelerate your reaction products. We've gotten to a fairly high rate of reaction, steady state now. This is not pulsed. This is steady state and goes on for minutes. In fact, it can go on for an hour at a time or more at this point. This is about a milliwatt, if I'm not mistaken, power that you see in that last picture. The availability of helium-3 is well documented. We've seen it in all the samples that have been brought back from the moon. We know a lot about its distribution because it is co-located with high concentrations of titanium due to its retention in the mineral ilmenite, again, iron titanium oxide. Current estimates are that if you take the moon as a whole, which you wouldn't do, you have down to 3 meters, about 1 million metric tons of helium-3 embedded in the lunar soil over the last 3 or 4 billion years. And the geology of those soils is really well understood. If you were an economic geologist looking at this, I think I could convince you that we know an awful lot about the lunar regolith based on the landings we've had and based on remote sensing that's been done since. The significance is that 1 ton of helium-3 can produce 10,000 megawatt years of electrical energy. That's a lot. That's about what a city of 10 million people will use today in a year. So some 40 tons, looking again this for 2000, of helium-3 would have provided for our entire U.S. electrical consumption during that time. Now you would never expect to have to take charge of that market instantaneously. You would enter it slowly as new plant and was required and old plant was retired if you could compete with existing sources of energy. Now, another way to look at the value of this helium-3 is that, again, if a plant existed today to use it, the value of today's oil prices would be of a metric ton of helium-3 would be about $4 billion. So maybe with that in mind, it's about time we took another walk on the moon. And with that, I'd be happy to take any questions that time permits.
Evidence that the Chinese are looking to go to the moon in a couple of decades. What do you think that they will probably be looking for there? And based on your experience in the U.S. Congress, what do you think will be the political ramifications here in the States?
I strongly suspect that their primary motivation is national prestige and competitive with the United States in some way. But the fact that they seem to be talking about the moon in some of the ways they have, I wouldn't be a bit surprised that if the truth were known, they probably have a lunar resource initiative in mind as well. Certainly the Japanese have been active in this field since the potential of helium-3 was first identified by the University of Wisconsin folks at under Dr. Kolsinski. And I suspect the Chinese have pretty well been monitoring that as well. We don't know. We meet with the Japanese regularly, every 2 years, on the fusion technology side of things. So we know, we have some insight into what they are thinking and doing. It's an important part of their thinking relative to their lunar program, which they've had in mind for some time. We just don't know whether this is something the Chinese are thinking of. It's not going to surprise me if they are very familiar with what's been going on in the open literature on this subject. I can't tell you whether the United States Congress would react the way it did to the launch of Sputnik, and then to support the President Kennedy after the launch of Yuri Gagarin. I just don't know. I don't know. It's awfully hard to predict, as I talked to some of you earlier, how the political system is going to work at any given time, or not work, as the case may be. And that is the reason I have looked much more, because it's more predictable, I think, and I can at least target what I have to do at getting the private sector involved to get back to the moon. It just, if you do your job right in business planning and implementation, then you can keep investors interested in what you're doing and have a sustained commitment by investors to interim as well as long-term returns on investment. I find that a little easier to tackle than trying to figure out what the government's going to do next. And so that's where we've been putting most of our effort, is trying to put together the business plans for the early businesses, not the lunar. We have some general strategies for the lunar power initiative, but mainly we've been looking at how you use these electrostatic fusion devices at low power levels for useful purposes here on Earth. The first one we're looking at is not very far away in terms of technology, and that is to have a 1-watt device that can produce positron-emitting isotopes at the point of use for PET, for positron-emitting tomography, and where you can't do that today. Today, the isotopes used in PET diagnostics are produced by large cyclotrons in large urban areas. The one of choice today, fluorine-18, has a 110-minute half-life, which you can transport at a few hundred miles, but it starts to become more difficult. You have to have a large excess to transport it much farther than that. There are other positron-emitting isotopes that we can handle that have about a 10-minute half-life, nitrogen-13, for example. And that is very attractive because, unlike fluorine-18, it can be used in diagnostics for pregnant women and children, whereas fluorine-18 cannot be used that way today by regulation. So that's our first business we're looking at. There's some others along the way as our power levels would rise. Probably one of the more interesting ones, even before you get to break even with these devices, is having enough proton fluence that you can begin to systematically transmute radioactive waste. It's going to be an interesting engineering design to how you get the flow of the waste past your proton fluence, but I'm satisfied that engineers are clever enough to figure that out. And we haven't started to work on that yet. We've been primarily focused on the positron emitting isotope production. Brad.
Jack, NASA is in a time of fair distress right now. I'm wondering what you might offer to Sean O'Keefe as advice on what he should do.
Well, I'm reluctant to give anyone advice. However, it was the advice I gave this administration in mid-2001, and that is that, and one of them they're doing now because they have to do it, and that is a Delta flight readiness review of the space shuttle. Unfortunately, it was not done earlier, and who knows whether they would have picked up that flaw or not. But it certainly was clear that there are enough things that happened to impact shuttle operations that it was time to take a deep breath and look at it. This was 2 years ago. The main thing that I think Sean O'Keefe has concentrated on what everybody thought was job one for NASA, and that is to fix the financial management system of the agency. But there was job 2 and 3 as well that should have been taken on at the same time, and I just don't know whether that has been. And one was program management. NASA had forgotten how to conduct program management. They were paying bills to major contractors without looking at what milestones and others, if they didn't have the milestones, for one thing, take the X-33 for example, and they'd forgotten what program management meant. And also in a more, the NASA had forgotten what risk management meant, and that both from the technical and the financial side of things, how do you manage your risk? And they just weren't doing that. Now, whether that is being done now in the agency, I just don't know. But if I were to advise the administrator at this point, I say you've got to focus for the long term on the financial, the program, and the risk management systems and get them up to speed so you can indeed manage these large programs and manage them with minimum risk. I would have had an entirely different space program had I been asked in 1972 or 73, but that's water under the bridge now, and you have to use what you have as long as it is reasonable to use it and look on to the future and see what can be done. I don't know that NASA can get the sustained support as it exists today for a return to deep space. I suspect they'll be able to sustain support for continued operations in low Earth orbit and space station operations, but I don't know how right now you put these things together. Now maybe a significant initiative by the Chinese will stimulate other thoughts in the Congress and in the administration. We'll just have to wait and see. Yes, sir.
What kind of professionals do you think NASA should send to the moon if they were to return? Pilots, engineers, or geologists? What do you think, knowing what they know now about sending pilots and geologists?
Well, let me take that from two perspectives. If you were going to fly an Apollo 18, I think that with the 3-person crew and maybe a few more days, I think the mix of a pilot and a trained field geologist is a good mix. And because particularly if the pilot is as willing as most of the commanders of the last few Apollo missions were to learn a lot about what observational field geology is all about. You can't substitute a decade or two of experience in a short period of time, but you certainly, with test pilots, you're dealing with good observers anyway, people who are well educated and bright to begin with, and so I think all the teams were pretty good teams. I can only speak for the two I worked with, Dick Gordon and Gene Cernan, and I think we did about as much as you could expect to do under the circumstances. Now, if you begin to look at much longer duration stays for scientific purposes, then you clearly will have pilots. You'll want pilots to get other specialists there and back, but you'll probably get more into the kind of operation of a space shuttle program where you have a bit of a dichotomy between the pilots and the other professionals that will be doing specialized tasks. And that same probably applies to if you do it with a private sector effort, is that the private sector corporation would probably be hiring pilots as their routine operators of spacecraft back and forth to the moon, and then have maybe even more diverse specialties than even NASA would consider, ranging from people who can operate highly robotic but still not fully robotic mining systems, processing systems, as well as geologists, you can call them economic geologists, you will, who are doing the precursor planning, mine planning, and that kind of thing. It becomes a much more sophisticated operation with a wide variety of skills required. Engineering design, for example, for any, I think, corporate effort on the moon is going to include not only a focus on robotic operation of equipment, but also on embedded diagnostics, just-in-time maintenance, a whole bunch of things like that that have to be done so you don't stop operating, because you're going to have contracts to fulfill back here on Earth. It creates quite a different perspective, I think, on how you engineer things when you have to think in terms that everything I do wrong is going to cost me money and cut investor return. It's an interesting new way to look at it. I never looked at things like that before until about 10 years ago, and I started to think along these lines that it might be more predictable than working with the government. Yes, sir.
Do you have any idea when the San Francisco mountains were geologically active, the Flagstaff?
Oh, that is known. I know the last eruption, namely Sunset Crater, was in 1066. I think they heard about the Norman invasion and decided to erupt. But that has been an active field for millions of years earlier than that, and I just don't know the exact numbers. Clearly it was active before the last major glaciation, because there's a great glacial cirque in the top of Mount Humphreys. If you've never been up there, it's really quite a spectacular place to hike and climb, is in that glacier that actually fed out to the northeast, I believe, from the top of the mountain. Yes, sir.
Standing on the moon, what was your most memorable impression, I guess?
Standing on the moon was my most memorable impression, was probably standing on the moon. It was certainly not something I anticipated doing before November of 1964, when I saw the announcement on a bulletin board in Flagstaff that NASA wanted scientists, astronauts to apply. I'm not sure they wanted it, but at least the National Academy said they wanted it, and it all worked out. That was not something that I had planned to do, and I've often advised young people that's one reason why you've got to try to get as broad and as detailed simultaneously education you possibly can to be ready for the next opportunity that you don't know about. And fundamental to all of that is having a background in mathematics, because it's the language of opportunity in any kind of technical or scientific field. And it should be thought of as a language. If we don't see, and I doubt if there's anybody in this audience that doesn't agree with this, but I think that one of the biggest things we do to hurt young people today is keep them from learning mathematics at any time when they're young as a language. They don't have to use it, they can often do other things, but if you don't have it, you've eliminated a whole spectrum of professional opportunities in the future that you'll just never be able to grasp. But meanwhile, back on the moon, I suspect that the full realization of being there did not really click in totally until about 30 minutes after I was outside the spacecraft and had a chance to move away from the Lunar Module Challenger and to take the first set of panoramic pictures that we wanted before we totally trashed the place. And that was the first time I was able to see the lunar module in the context of this immense mountain valley. We were in a valley deeper than the Grand Canyon. The mountains on either side were 6,000 to 7,000 feet high. Black sky, brilliant blue earth, and of course a brilliant sun, as bright as any sun that you can imagine. And to finally have a chance to see all of that while I was taking this panoramic picture was really probably when I first, the impact of being there hit me. It didn't stop me or anything like that, but you start to absorb those kind of things at that point. Prior to that, I was dealing with a spacecraft that I was very familiar with. I'd worked around in the test bays at the Kennedy Space Center. I'd worked with many lunar modules, and particularly this one in the past, so it was not, and your field of view is always restricted a little bit in those helmets, so I was looking at an old friend, at somebody, and I was working around it, and I hadn't really seen what I was going to see until I moved away from that spacecraft. And that was really, it was quite an event. Yes?
Just curiously, from your personal perspective, how do you feel about the fact that that little cabinet behind you has like infinitely more computer technology than what you put your wife in to get to the moon?
I'll take responsibility for it. No, you know, Apollo just sort of triggered a revolution in data handling, data processing, information, and the like. The Draper primary guidance navigation system, the pings that we use to go to the moon, was barely a calculator. And most of the computing was being done by several floors of IBM, what were they, 3300s at that time, or who knows? But huge IBM computers down here on Earth, and the results of that computation then fed into our computer, which was just capable of using it for extraordinarily precise landings. So it was certainly adequate to the job. We landed within a few tens of meters of where we planned to land on every mission except Apollo 11. And would have landed, had we just let the computer take us exactly where it wanted to go, rather than taking over manual control, we would have landed essentially right where we planned, the spot. But usually there was a boulder or a crater at that point, and you wanted to move away from it. It seemed like a rational thing to do at the time. Just an example of what we were dealing with, some of you may know that we were delayed 2 hours and 40 minutes in our launch because of a computer glitch. Is one of those garbage in, garbage out things where, for some reason, in the launch control computer, way back in the Lost in the Dark Ages, the computer had been told in the final countdown checks that occurred at 30 seconds to look and see if a tank had been told to be pressurized rather than whether it was pressurized. And when it went through that, at an earlier point, through that control, the tank, one of the oxygen tanks in I think the S1C stage, had been told to be pressurized. It didn't react to that command from the computer, and a launch controller saw that happened and just punched it and manually pressurized the tank. So the tank was perfectly all right. It was pressurized, ready to go, but the computer didn't know it. And so at 30 seconds, it finally said, I'm not going to let you go. Well, it's just what you wanted it to do if it wasn't sure. But you can see that it was looking at the wrong parameter. Why it wasn't told to look at a pressure transducer in the tank, I don't know. But that held things up for 2 hours and 40 minutes, most of which was time it took to convince NASA management that the people knew what was wrong. It didn't take very long to figure out what was wrong, it turns out. But to solve it, what they did was just went into the computer and hardwired around that particular junction. I don't know exactly what I'm talking about, but they actually hardwired in that computer around. These are huge banks of computers, and they found the place and hardwired so that as far as the computer is concerned, everything was hunky-dory, and the next time we went through 30 seconds, off we went. Yes, sir.
Looking back on Apollo 30 years later, what's the most surprising or most unexpected thing about the legacy?
I think that just about everything that I mentioned in my early charts, except the having met the Cold War challenge, would have to be considered a surprise, because if you go back and look at what was being thought of in 61, 62, 63, we weren't thinking that we would ever get those kinds of things out of this mission. There were a few people like Gene Shoemaker, Harold Urey, and a few others who on the science side felt that this would just be an amazing bonanza, but the vast community really wasn't paying attention to this. The idea that we would find resources on the moon that could support space civilizations, nobody talked about that I can remember at the time. In fact, the importance of helium-3 wasn't recognized to future energy supplies, wasn't recognized until 1985, when some engineering physicists stumbled across it in our literature, which had been there since 1970. The people interested in solar wind physics had measured it, because that's where it came from. And they knew about it was there, and they went about their papers, wrote papers on it and everything like this. But their interest was in solar wind physics and not in whether it was a resource or not. And then once you start to look at that, you realize, well, there's hydrogen there too. And that, from hydrogen, you can make water. And you have the oxygen, of course, in the rocks. So that was totally unanticipated. People just had not thought about that. And from the evolutionary status of the species, I never heard anybody talk about that until well after Apollo was passed. So clearly the objective was made. That's what everybody signed up for, is to land on the moon. And fortunately, people like George Lowe, some of you knew George, and Bob Gilruth, Sam Phillips, and Werner von Braun, they all sort of had this vision that we were going to do a lot more with Apollo than anybody thought we were going to do. And frankly, I think that began to be obvious when you realized that the lunar module and the Saturn V and the command module were all way over-designed in the final analysis to just land on the moon and come home. The lunar module actually, right from the very beginning, the first design reference mission that Grumman did, had a 4-day stay. Von Braun, he'd give you a little bit more for every mission. But at the beginning, nobody thought we would put 44 metric tons on a trajectory to the moon with a Saturn V. He may have, but he didn't tell anybody about it. And you had to squeeze every metric ton out of him for Apollo 8, Apollo 10. He'd give you a little more for Apollo 10, a little more for Apollo 11. Had some secret little supply of thrust that he had over here, and he kept giving you a little bit more. But for Apollo 17, it was the heaviest payload, and it was 44 metric tons to the moon, and that's a heck of a launch. We had that for a while. We had that kind of capability. One thing just to think about, and then I'll stop because I know Wes is trying to give me the hook here. But for a very brief period of time, between 1968 and 1972, we had the capability to do something about an asteroid or comet that might be on a trajectory to impact the Earth. You don't have that capability now. Technologically, you could recreate it, but you don't have it. So we're in a very unique position right now in terms of human civilization. There's still a major debate and major discussion, and I don't know what my opinion is on whether, how much investment you make in extraordinarily low risk but extraordinarily high consequence events in predicting and in preventing such events. But at least we are at a point right now where we can have that discussion, and it's a realistic discussion. And that's one of the side benefits of some initiative that gets us back to the moon is that you also create this capability again and create it indefinitely, because you're always going to need heavy lift launch to work in deep space. Ladies and gentlemen, thank you very much. It's been great to be with you. Hope you come back.
Jack, we sincerely thank you. As a geologist, a pilot, an astronaut, administrator, a business person, a writer, and a senator, you have certainly provided us with a very stimulating account of what happened on our way to the moon and what our future may be like. So thank you so very, very much, Jack. I would also like to take this opportunity to say thanks to two people who really guided us to this particular event. Professor Earl Merman and Peggy Uten. Thank you both very, very much. And to our audience, again, thank you for coming and for your stimulating questions. This concludes the 31st Lester Gardner Lecture. Thanks again.